we'll stop it there. Oh. There we go. Hello, everyone. Welcome to our second class meeting for CDM ECS 12 Media Computation. Today we're going to be talking about readability, color, and transformations. So what you just saw was from the demo scene. Does anyone know what demo scene is? Ooh, yeah. Yeah, so it's a group of computational artists who make compelling audio-visual experiences, typically with the smallest amount of code possible. So a lot of these range from artistic expressions like you see here, which play both color and sound together, to procedurally generating architecture and worlds for you to experience. So demo scene is an interesting form of art that brings people from the art world and from the computer science world, from the programming world, into the realm of interactive media or film. So it's an interesting example, particularly this 2021 entry that won a few awards, I believe, by Ninja. I'll give you the slide so you can look through the YouTube link and things yourself. It's an interesting community. The meetups are really fun. All right. Great, I'm recording. I think we're getting full audio. Excellent. All right. So I want to start with some bookkeeping today. So let's hop over to my browser. One moment while I make sure I have the correct tab open. And great. Okay, so what we have here are our announcements. I sent an announcement around 9 a.m. this morning, and it has some basic information about today. Just doing a quick check. Okay. Now, today we have our first lab. So we'll have our lecture today until 11:50, then we'll break, and I'll furiously ride my bike over to the RDNX to set things up before you all arrive. At 12:10 to 1 o'clock, we will be having a lab. And this lab consists of a small assignment that can take you anywhere from 5 to 25 minutes, depending on your skill level, comfort, how much stuff you already have installed. And you'll notice that that time is dramatically less than 50 minutes. So what do you do during that 50 minutes? Well, we're here to help you learn the basics of processing. This will be some of your first programming experiences, so we want to make sure we have plenty of help for you. And it'll give you time to get started on assignment 1, which is due on the 11th of October, 11:59 p.m. It's a Wednesday. So for those of you who are curious, the RDNX, we have a campus map locator. I think I asked last time, who's been to the RDNX? All right, so you may want to follow someone, if you didn't have your hand raised, follow someone who had their hand raised on the way over. It can be a little tricky to find, but it is close to the library behind the art building, a little parking lot. Here's Marac Hall. You'll see a lot of egghead sculptures here. So feel free to check that out. Please do that. Please bring your devices. This will be a time for you to work on your code, show us code, work on the assignments in the lab. We want to see it. So for the lab, I'm going to set up a submission section on Canvas for you to upload your files. That's how we'll be rating your content for the course as far as assignments and labs go. We will be seeing your uploaded pictures. We'll show you how to take pictures, screenshots in processing, and we will be looking at the code projects, the actual processing project files plus the code. All right, so we will be at the screening room in the Art Annex. There is also an accompanying Mac lab, which is just down the hall. For those of you who need computers, you ran out of batteries, you forgot to bring your laptop, you need a device at all, there will be machines that should have processing on them installed, let's hope, today. All right, so Just a reminder, labs are worth 6% of your final grade. The first 6 labs will have content for you to do worth 1% each. After lab 6, we'll be primarily helping you with your group projects, studying for midterms, working on answering technical questions you have. That'll be the theme. So the grading will be a little front-loaded. All right. Assignment 1 should be released today. I will give out the assignment file. I think there's a portion Canvas for it already. I realize most of you are used to having all of the class scheduled stuff inside of Canvas. I historically really haven't done that and have made my own schedules because I don't like dealing with Canvas. But since I usually keep upper division courses and you are mostly lower division students, first year and second year, I may make an exception and just dump everything into Canvas, which I probably will do that. I'll make it easy on you. All right, so assignment 1 is worth 5% of your total grade. This is it's a light assignment. It has 3 sections. We'll go over it either at the end of class or in the lab, depending on how time looks today. I think that's about it. So for those of you who had problems with Canvas, those should be resolved now. Does anyone not have access to Canvas at this point? Yeah, that's what I like to see. No hands. Excellent, excellent. All right, well, great. We have it cross-listed. The instructor issue is worked out. Great. So if you look at the syllabus, you'll see there's a full schedule. We'll flip to it in just a moment. There are some things that are subject to change on there. We'll see how this class goes. Please join Discord. So for Discord, once you join the server, you'll see that there's a bunch of stuff going on in this Discord. It serves as a community hub for some computational media work here on campus. So I do my research with my research labs here. I include undergraduates on game projects and graduate students on master's projects on the server as well. And you'll see that there's several classes that I teach here. Gameplay programming, which will have its own course number. That's an upper division computer science course aimed right at making games. We have game platforms, which is a topics class in CDM, which may be its own class soon. That class involves creating games in the Pico 8 retro fantasy console. So you're making games in an older style with the same setup, actually, the same basic breakdown of tasks that processing uses. So it's a good transition course from this to game platforms. We'll also be reading the platform study series. It's a game study series of books that revolve around particular game platforms such as the Wii, the Super Nintendo, Flash. So there are in-depth holistic inquiry around each one of these platforms. And we'll be reading some of those books as well and making media projects about them. And I often teach a research topic on computational storytelling, which involves artificial intelligence blended with narrative, character, and story interactions. So that is a nice passion class of mine that I really love teaching. And finally, here we are on this list, ECS CDM 12 computational media. To see the channels involved with this, you simply react with art. No roll. So you make sure this is highlighted. And you can check out the other classes too if you want to click the links. You can go in and out of the class just by toggling the roll. All right, and I see a bunch of people have joined. Excellent. Oh, I guess you can't actually see what I'm, darn it. Okay. I'm actually doing extended screen, so let's see if I can have the coordination to pull this off. So welcome. Here are the courses I mentioned, and this is the toggle. Hey, look, that number go up. Excellent. So I'll be answering questions on there. I'm pretty responsive on Discord. DMs a little less so because I have a lot of DMs and a lot of incoming message requests, and triaging those gets to be a lot sometimes. So ask questions directly in the channels if it's not personal, and if it is personal and it's class related, particularly to you, and you don't want other folks to know, email is the right form for that, not a Discord DM. All right. So I'll be sending out a survey, hopefully this afternoon. Got a lot of stuff to do. So I want to see when is good times for office hours for you. I have some candidate times pooled in my schedule, and I will be sharing those with you, and you can vote on which ones you like the best. Probably like a when is good or something like that. We are looking for tutors for the class as well. So if you know any folks who want to get a little engagement with courses, want to help other folks out, are angling for like a reference or a letter of recommendation for something media related or computer science related, this is a pretty easy course to tutor for if you've had some programming experience and knowledge. So I want to get more facilities for helping you all out. All right, I think that's it for this. Let's take a look at the syllabus. Oh, that's assignment 1. We'll look at that in a bit too. But here is the syllabus. Going through, we've looked at all this before. We've looked at the grades. You can see the assignment 1, 2, 3, 4, 5, and 6 are all worth different amounts of points based on their difficulty and relevance to the course. This one, I wanted to make sure that you had a fairly, in your first assignment, your first programming thing that you turn in that has a larger score attached. I wanted to make sure that had a little less consequence to it. So the 5% is worth half of the median value of assignments. All right. So here's the schedule. I'm assuming a lot of you have looked at this. So we have the week, the dates of the class meetings, the topics we cover, the readings associated with that day. So those are the days that we're covering the topics. We begin covering the topics in the reading. So for those who want to be prepared, you want to have the reading done by the time you enter class for this day. Like for the next class meeting, we're looking at chapter 4. Chapters 1 and 2, the bootstrap week is the exception. We're covering a lot of what chapters 1 and 2 tell you in lecture. We're not covering everything in the book, but you are responsible for that material. They are fairly light chapters. This is a very easy, a lightweight introduction to programming. So please read it if you have questions. Happy to answer them. We'll be giving out assignment 1 today, due on the 11th, so the Wednesday of next week. We're going to cover some syntax, saving images, and moving objects today, how computers work in variables on Thursday, and then we'll start moving into conditionals and interaction and loops. So we're going to be moving through class topics, about one major chunk per class meeting. Hello, Preet.
Josh.
Excellent Kirby hat.
Thank you. We're going over the syllabus?
Yeah, we're going over the schedule now, just like we did last night. All right, and so you can go through here. Some things to note. I've tried to keep all the due dates consistent to be Wednesdays. That way we can have load some extra office hours perhaps on Tuesdays and Wednesday early to help you out. But I'm sure all of you will do the work before the last minute. No worries. We're going to look at image manipulation. We are going to have project proposals. So assignment 6 is different than 1 through 5 in that it is a group interactive media project, which you'll be working on folks together. You'll give proposals for. I'll give you examples on how to do this and the scope of what we're looking for. And our last 2 class meetings will be the presentation of those materials. So you'll be up here chatting just like I am. And then finally, our finals meeting time will be for the final exam itself. I'm going through the SDC requests. Please submit those if you feel like you need them. They're excellent resources. I'm already going to be sending a few exams to SDC for testing accommodations such as extra time, folks to help read and process the text, that sort of thing. So please take advantage of those resources. I want you all to succeed. November 23rd is Thanksgiving holiday. That it should be our only break from class. After the midterm, I should be out of town for a little while. Since I'm covering this course, I had a lot of conference and research travel planned. So I have to do that as well as keep the course going. So we'll likely see some guest lectures, maybe even 1 or 2 from your illustrious TA. And so the midterm, depending on how my travel plans work out, I may bump that up to November 2nd instead of November 7th. Either way, we'll have catch up and review. We'll have a class section dedicated to studying for the final, to review and cover material that you don't feel as confident in or need a refresher on. Happy to do it. All right, any questions about the schedule or logistics before we get into the content of today's lecture? NRP, could you get a rough head count, please?
Yeah.
Thank you. The reason I'm asking for a head count is I am recording this and I want to see like what attendance is like. If I post videos, I want to make sure attendance does not suffer too much. But I want to try to give you as many resources available while keeping you in the room. Okay, well, I don't see any questions. I guess it was straightforward enough. Yes?
I was wondering where we could find the review.
Oh, you can look on the syllabus, so you can go here. This is the text, Learning Processing, Second Edition, A Beginner's Guide by Schiffman. So the chapters are all from this book. You can get them at the UC Davis Library. Here you go. It's available online for free. You can actually download the entire PDF from the site. Check it out. Like eCentral Academic Books Complete. The first link has all the stuff you need to know. You can read it online, download the pages. So for instance, if you read online, you can write the table of contents. If you want to read lessons, so the lessons are different from chapters. So if you want to read chapters 1, you go to lesson 1, chapter 1, pixels, processing. So you can see all of these, like chapter 2 is 9 pages or so. So they're all very, very accessible here. Did that answer your question? We good? You're welcome. Anyone else?
I have an answer for your question.
One moment, RP. Oh, did you take the rough head count?
Yeah, 73.
Okay, thank you.
I'll write it down.
Appreciate it. Okay. I think we are in good shape then. Let's move back to the presentation. All right, so we got done some bookkeeping here. So we've synced up on some of the classwork. All of you now have access to the information sources. My apology for not having those on day one. This crossover handover of the class from another instructor and myself did not go smoothly at some levels of the administration, so here we are. Okay, so drawing practice. Oh, let's see here. Why did that not change? One moment while I fix the font size so we can all see it. Great. All right. So rect mode. So you can handle some of this. So this is a little bit of leftover from last time. This is a slide from last class. So we want to specify how rectangles work. So there are different modes that rectangles can work in, whether you want to start drawing from the center of the rectangle or from the corner of a rectangle. Right, we had some examples from last time. This can really help you in composing scenes. So if you want to be 0, 0 origin on the top left grid based, that's very handy. Or let's say if you want to draw something that is very easy to center and you don't have to do the math for it, you say the center should be here. That's what rect mode center can help you do. Ellipse is the same way. You can either do width and height for ellipse mode or have the center of the ellipse be your first two parameters, the x and y coordinates. So if you want to draw a circle, just make the width and height the same and use ellipse. So I will be sending out some drawing examples soon. We'll look over maybe some of these in the lab. Yes?
Sorry to interrupt you, but are
Yeah.
you going to be uploading the slides on Canvas as well?
Yeah. Yeah, I'll be uploading slides from last class and this class to Canvas. You're welcome. And that's good because there's a lot of copy and paste examples that you may want to play with on the slides, and they're sort of like designed for that. And in the future, I'm hoping to give you the slides ahead of time. I'm still processing through them and getting them all prepared for you. All right, so if you wanted to do, like you wanted to draw this circle here with eclipse, you can put in the x and y value. So the x value, if this is a 400 window, looks like it's around 350. The y value looks like it's around 100. And the width and height look to be perhaps 25 each. Right, so you'd fill those values in instead of the left angle or the less than x greater than. You should be good to go. All right, so that was just a little bit of review from last time, and we'll go over more code examples in class. But if you want to dig into any, we have the code ready to go. I want to show you a little bit about the editor and how to configure it as well. All right, so we're really talking about chapters 1 and 2 here. So that was for yesterday's lecture. Today's lecture, we're continuing on. So writing clean code is, there we go, presentation. I don't have my keybinds all set up. I don't have my number pad with me that I usually use. So writing clean code. This is important. So you want to be able to read your code later. You have a blank page to work with. You can make your code be weird and indented. The interpreter actually gives you a lot of leeway of white space and tabs. So you can write things like correct, 100, 100, 50, 50, right? You can make it look pretty standard. It'll also properly parse things that look like this, right? But that is very hard to read. You don't know what the intent is. This is you formatting your code in consistent ways that you'll see in class is very handy for you in your future readability, you working on assignments, and us properly grading. I guess you can't see the drop down. Control T is auto format. So if you press Control T, it will try to do its best to make your code legible. So like if we had this, Control T, it would correct the spacing for us. So this auto formatting tool will be very handy. It doesn't fix everything. So you want your code to be in a space where it can do tweaks to your formatting and not have to completely rectify an entire function of a set of code that is really sketchily formatted. Like you saw when I had the line breaks, it tried to do this, right? Which still is bad. This is what code formatting does if I have weird line breaks. So this is about syntax. So many of you have had, I imagine all of you have had courses in syntax, particularly in maybe middle school and elementary school, where you took a sentence and you created a tree from it with subjects and objects. You're parsing out the portions of the sentence that have meaning to each other, right? Well, those trees are exactly how processing reads your code. So if we have our example, if we go back to our example here in the code editor, we have our rectangle command, which takes its parameters. So the parse tree of this would actually be like, okay, this is a command. And then it would branch down into the name of the command and then its parameters. And the name of the command would be rect. And the parameters would then have the beginning of the parameter list, which is a paren. Then it'd have a parameter list inside of it, which would be 100, delineator, comma, 100, delineator, comma, 50, delineator, comma, 50, and then pop back up and do end of parameter list, close paren, and then end of command, semicolon. Right, so it really does break these things down into a tree. So every bit of text you have on here has to be understood in context of processing programming structure. And we'll talk about a lot of that today, but we won't really make the trees ourselves. They're important to understand. They're important to look at the documentation. This is a look into how the machine interprets your text. But this is not a programming languages class. Computers are uptight, like your grammar teachers. So everything has to be very precise. And there is not really a good sense of spell checking, although that may be changing with the large language models that interface with code. What they will do is help you format, like the auto formatter, but the actual meaning that you want to convey through your code, they don't know. So that is something that you need to think about at a high level and then try to state it precisely. So a lot of learning how to program is learning how to communicate with something that is very pedantic and not nearly as a round thinker as you are as a human. So you have to say everything painstakingly and precisely so it knows exactly what you're talking about. So really computers are stupid. The design of machines is very brilliant. There's a lot of innovation that has went into making something that runs billions of times, runs instructions billions of times of seconds, formulating zeros and ones, all the way through to that media experience that we saw, through virtual reality, through the stuff happening on your phone. It takes a lot of clever human design to work around the rigid but very fast way computers see the world. Ambiguity is tough. Computers are not good contextual decision makers, so you want to be very explicit when you deal with them. If you don't understand what's going on, chances are it won't either. So one thing that helps out for this particular programming language, so processing is based on the Java programming language. So if you learn the syntax for this class, you'll have a good foothold into learning something like Java, or maybe even C# for work in Unity, or Godot, the two game engines that are popular now, some more vilified than others. So rectangle, our command, right? It has a semicolon at the end. That tells the Java parser, the processing interpreter that's looking at your code and trying to figure out what's going on. It says, okay, the command is done. We are finished with drawing a rectangle. There's nothing else I should interpret on this line. So that's sort of like the period at the end of a sentence, if you were drawing that sentence tree. Now you'll see a lot of funny things that you don't normally see a lot of in English. So the left parenthesis and right parenthesis are for commands, for parameter lists, such as rectangle. You could also use them with math to parenthesize as you would in arithmetic or algebra. But primarily we'll be using those to say, hey, here's a command like rectangle. What do you want to do with the rectangle? What information does the rectangle need? And that information goes into a comma separated list in between parentheses. Now the curly braces. These are a fun one. Like you don't see these a lot in normal writing. They are for blocks of code. For example, our draw command that we've talked about that updates once every frame. So this will, how you can have change over time, this will happen like 60 frames per second typically. So 60 times a second, this draw function will be called. And everything in that draw function, everything in the draw function's block of code will be ran. Now, how do you associate a block of code with draw? Well, with the curly braces that go right behind the parentheses. Everything within those curly braces, every bit of code you write, every command, is considered part of draw's block of code. And you'll be seeing this a bit too. We'll That'll be something you'll become quite familiar with. We'll use those in conditionals and iteration, if statements and while statements, for loops. Now, the square braces are for arrays. And we'll be talking about those soon, but this is how you get one variable to point to many values. But not for now. There's a little bit we need to learn before then. All right, any questions about this? These are kind of tough to enter on virtual keyboards, so I recommend you have some real keyboard, like if you're doing these on some sort of Android device. I recommend that you have an external keyboard available for it, a little Bluetooth keyboard or something. So when we talked about syntax earlier and being nice to yourself, this is really about human readability. So the curly braces, the left parentheses, the right parentheses, all of those are about the machine reading your text. That's half the problem. You reading your own text is the other part. So you'll be able to write it and then read it and edit it and draft it, much like writing an essay or making a recipe. You'll want to edit it, change it, fix it, tweak it. That's the heart of iterative code design. Now, white space. These are your tabs, are your spaces. So you want to leave white space between blocks. So for instance, on the setup command versus the draw command, as in our example from last class, there was a line break between those two. That's just to help you parse through and visually understand your code. Now, comments, we talked a little bit about, and these will appear in light gray in your text. What happens there is that those are signals to the compiler to say, hey, do not read this. Do not include this in your tree breakdown, your syntactic breakdown of what's going on in code. So these are where you can write your own notes to yourself, right in your code file. So if you use the double / like it says in single line here, that tells the compiler, hey, everything after this / for the rest of the line will be ignored. But hey, you may want to write something that's longer than a line. This is where the / comes in, /*, and then */. Everything between a / and a *// will be ignored. The beginning of the comment and the end of comment. Begin rant, end rant. Right, make sense? Pause for a moment. Any questions on braces, comments, syntax, parameters? All right. Now, here is what a bit of code looks like. So here you'll see a few things that we haven't seen yet. Let's talk about this just a little bit. So you want to indent all blocks for readability, right? So here, you want to think about indent levels. Every time you go inside of a curly brace and there's a new block of code, by convention, you want to have all the commands within that block of code be indented 4 spaces past what the block curly braces are. So 4 spaces for this, setting the stroke to 4 in setup. Okay, so I guess void setup, parenthesis, void we'll talk about when we go into functions. Right now you can just include it. Curly brace. So here's what setup does. Everything between this curly brace and this curly brace is executed at setup. All these commands are written. So the first command we have is the command name stroke. Its parameter list set everything between the left parentheses and right parentheses is right here. And that is 4, the value 4. So we're setting the stroke color to 4. And then we say, hey, we're done with this command now. That's all we need to do for the stroke command, semicolon to end that. And by convention, when you end the command, you want to start the next content on the next line. This is something you some of you may have seen in the wild, some of you may have already learned a little bit of programming. This is a for command, so this will run the body of this code a number of times, in this case 10 times. And if you want it for the code that you wanted to run 10 times, you'll indent it 4 more from the curly braces that denote the block of code that for should run. Right, so we have indented code blocks here. Now what's great is 4 is the default spacing for code formatting. So when you can control T your code, it'll automatically put things in 4 block spacing when they're indented. Let's take a quick look. Let's see, we had a little example. Yeah, we're just going to do this. Take a quick look at lab 1. All right. So here, there's some messiness in this code. Okay, this is by default set up to 2. Maybe I'll change the advice and make the default to 2, since that is what everything seems to be. Okay, there's plenty of tools. I'll give updated advice. I think 2 is probably the right answer given the size of the stuff you'll be working with. So here we have draw. So if we change the spacing here, we mess this all up. Oops, that V would not be handled, right? So notice when I put in this extraneous letter here, I accidentally pressed V when I was pressing a bunch of spaces. Now this is highlighted in red. Hey, it doesn't know how to parse this. There's a syntax error. It thinks there should be 2 commands here, and one is missing a semicolon, right? So this V is obviously something wrong, and you're going to get commands that may help or may need some interpretation. So this is one case where the computer is dumb. It says, hey, so it doesn't say, hey, you accidentally put a V here. So it doesn't know the context in which I did this. It thinks that was an intentional act and is trying to interpret it as well as best it can. So if I take the V away, it'll give you some real-time update here. So if I do that and then put a bunch of tabs over here, right, it's bad news. But when I hit Control T, it will go ahead and do the automatic spacing for me. There, and you can see this is what you're going to start with lab 1. It'll have no output. It'll be your job to give us some output, as we'll specify. All right. So the basic readability, it says, edit auto format. That is the command structure that you go up to the edit menu and do auto format, code format. Control T is the key, is the shortcut for that, and it'll do you some favors. Let's talk about color. I'm curious, how many of you have taken in your classes or through self-introduction, have you looked at color theory like RBG, CMYK? Okay, so we have roughly, maybe a quarter of the class. So maybe I'll want to go into more depth in this later. But for now, what are the primary colors?
Red, green, and blue.
Red, green, and blue. So it depends on which, so there's multiple answers to this. You could also have cyan, magenta, and yellow. Right, so there are different views. So there are lots of colors, right? So what our primary colors are sort of like what utility, they are a function of the utility that that color has for your use case, for your application, right? But those are the ones we learn about in grade school. So there are subtractive primaries, which look at the color space as a subtraction operation. So cyan, magenta, and yellow. This is what's used for print, right? Because for print, what you're doing is you start with a white, typically a white piece of paper is the metaphor, and you are lowering the intensity of that white. So if white is full on, all the colors displayed, full blast is the metaphor. Adding in cyan, magenta, and yellow helps tone that down into the precise color space that you want to have. Now we have additive primaries, red, green, and blue. This is the mixing light metaphor, or mixing paints. So this is what computer displays do. Computer displays do. They mix light together. So this is why often, and we'll use this in processing, our colors will consist of red, green, and blue values. So here is SIGGRAPH, a classic slide from SIGGRAPH. So SIGGRAPH is the ACM's special interest group on graphics. This is a big conference. Like tens of thousands of people go to this. It's in LA every year. Like all the Pixar folks, the DreamWorks folks, Disney folks, they're all there. Everyone that does 3D animations that wants to research and work at the high end, they typically have a presence at SIGGRAPH. So here is one of the explainer slides of my tutorial from SIGGRAPH about setting colors. Right? So we can follow some of the stuff we've learned in our art classes in primary school. Red plus green equals yellow, green plus blue equals cyan, red plus blue is magenta, red plus green plus blue is white. This is additive color scheme, also known as RGB, which if you're like me, you will say RBG a lot, notoriously, but RGB is the order through which you'll find these in the function calls. So in the high-end 3D graphics, highly performant library that games are often written in called OpenGL, or Vulkan is the newer version, you'll see that GL color 3F takes 3 floating point values, so numbers, with a period in them. So you can have decimals, not just a whole number, is what the F means. And it takes 3 of those. So you're setting the color. And you're giving it an R value, a G value, and a B value. So that's the basics of additive setting colors. Now here's what the color model looks like. So color models are actually 3D models. So you may have seen this in Photoshop, in Paint. You may have seen this hexagon looking color space. Now what's actually happening is that's a 2D projection of a 3-dimensional cube, right? So you're just seeing it directly on from this like white corner in the middle, right? So the front is white, that front corner is white, and the back corner that you can't see that's occluded is black. So the grayscale spectrum is that back-facing corner all the way through the front-facing corner that's in the middle of the color model. And you can see blue, magenta, red, yellow, green, cyan. So what you have here are these values that that sort of are in this cube space. And note that 1 in this model is full on, 0 is no color there. So 0, 0, 0 is black, 1, 1, 1 is white. Full red is 1, 0, 0, etc. Now we're going to branch from that a little bit, and you'll see why. Our colors instead of 0 and 1 to 0 will be 255 to 0. Where 255 is full on, 255, 0, 0 is full on red, 0, 0, 0 is full on black. 255, 255, 255 is white. And this is consistent with, for those of you who have ever used sort of like the hex system of colors, like on websites where you do like, pound or hashtag AA. It's the same space. Those are values from 0 to 255 in hexadecimal instead of decimal, which means there's base 16 numbers instead of base 10. The color gamut. How many of you have seen the color gamut before? Yeah, okay, so we got some folks who have been introduced to the color gamut. Those of you who have done the visual design classes probably have seen this more frequently than those who have not. So the color gamut, what you can see here, this space is the visible spectrum to the human eye. So do you see anything interesting here? Yes?
There's more of certain colors like green.
Yeah, what do you think that is? biologically, mechanism, evolutionary, contextually? Yeah.
It's easier to see like differences in plants and see different kinds of fruit.
Exactly. Like, how did we evolve? Well, we evolved amongst primarily green things that we wanted to pick from and eat from. So our world is full of greens, but there's actually not many blues in our world. And reds are more rare. So it looks like our eyes, the number of detectors for green in our eyes sort of like outweigh the others. We have more nuance in the green color spectrum, right? Which I think is pretty interesting, right? So the typical monitors, you can see, have the color spectrum of this large dashed line. The CMYK, the subtractive scheme that printing uses, is the lightly dotted line, the small dashes. And then, the monitors are the triangular one. The CMYK is this more slightly dashed, less angular one. And then the Pantone or hexachrome, you may have seen color spectrum runs is a little more round, includes a few more things. So now you can see that monitors specialize in this space to the right. So you can see these pictures. There's actually the Wikipedia article for color gamuts is actually pretty good. So it's a good place to go to for additional information if you so choose. Now, this is far from the full human visual spectrum. So now you can see why people are constantly like looking for ways to improve monitor fidelity, to try and get more of this color space with HDR, or color space visible at once with HDR displays, high dynamic and resolution technologies here. So that really kind of shows like where we can still go with our display technologies. So if you want to do like a lush green scape, you actually can't do the real world justice in the same way. Monitors just can't do it. Monitors and printing, green is still really tough. It's interesting how we've gotten much closer to true blue, which doesn't exist, it's very hard to find true blue in nature. Most things we think are blue are not actually blue pigmented. And we're closer on red, but the thing that we encounter most, we have the least amount to reproduce. We have the least capability to reproduce. So here's a few other gamuts that you can see. Some of you may have seen some of these over the years. You often see like printers, high-end color gamut spectrums, abilities to represent these colors, just because there's a like ProPhoto RGB has a representation for colors in this space. Doesn't mean we actually have the ability of monitors or an ink to reproduce those colors. Right, so some of these are theoretical color spaces, particularly the ones that go off the edge. Now we're producing blues that are not visible to the human eye. Moving to like ultraviolet territory. Yes?
So what does color gamut actually mean?
The color gamut, so the big blorb that you see here that has a lot of green on it, that's what the human eye can see. And our models are not perfect, our inks are not perfect, our oils are not perfect. So we have like subsets of that space that we can actually put down or put on a screen. And that's what the triangles and things are, what particular technologies can do. So this triangle is what RBG can do for us. This is what we'll be working with. But just to reaffirm, this is actually a 3D object, the color gamut, because there is luminosity. So completely dark shaded values are at the bottom and light shaded values are at the top. So black's at the bottom, white is at the top. And it's interesting because this is what we can see. So as we get closer to dark, we actually have a much broader range of seeing. So the base here is fatter than the top. So as things get brighter, we perceive less color. And I thought this was pretty cool. All right, let's talk about putting this into code. So once again, to reiterate, name is the name of the command that you want to do, in this case, line. And then, name here in the syntax that we're looking at are values that you need to fill in for a command. So these are helping you these are reminders for you of how this parameter list or this list of information that commands need, what they actually mean. So in a line, you want to go with the starting points of x, the starting x location, starting y location, and then how far you want to draw, where the end of the line should be in x and y coordinates. So this is a two-dimensional line, right? Like you would draw on paper. Now coding color and processing. So as we talked about, color is defined by a tuple, which means just a set of things. 3. Red, green, and blue. 0 is none of the color, since we're using additive color scheme, and 255 is as much color in that area as we can place in. So some examples here. Bright red is 25500. Bright yellow, 255, Dull yellow, 100, 100, 0. Mid-gray, 120, 120, 120. So all the colors are in the same proportions, which makes something grayscale in this scheme. And this is what the fill command takes. So the fill command is what the internals of your circles, of your rectangles, of your ellipses, circles, and rectangles are. In this case, they would all be that the fill that would be set for your subsequent drawing would be no red, no green, and 200 out of 255 blue. All right, any questions at this point? Stop for a moment. Yes?
So the range for like the red, green, and blue is all like 0 to 255, right?
Exactly. For each one of those values. Yes?
The fill command also uses the one-digit black and white gradient, right?
Yes. Yeah. So we'll look at the documentation. You'll see there's a version of fill that has 3 parameters. And there's a version of fill that has 1 parameter. And by the number that you give it, the processing knows which one to use. Question? Did you have your hand up? Okay. There's a 4th parameter version as well. Thanks for queuing that one up for me. All right. A for alpha. This is how transparent the color should be. Right now in this image here, you see that the red and green overlap, and there's a more muddy browny orangey color in here, right? Well, this means that the green is actually a little bit see-through. And this is also a 0 to 255 value, where 0 is fully transparent. You can't see any of the color shading at all. If you have an alpha value set to fully transparent or 0, it will be whatever color is under it. It will not bias it. There will be no color mixing. But as you bring that up, let's say for this green rectangle, the more green will be blended with the red. And this is stacking. So for an alpha to matter, the red had to be drawn first, and then the green had to be drawn over it. So if something transparent is drawn after or on top of anything else, that transparency will be mixed through it. I don't know, like, do people, I haven't seen this in years, but have people been using any transparencies on, these dock cams? You've seen, little overlay sheets, little cellophane sheets? Maybe I'll find some of this. That'd be fun to do color mixing, old school. Anyway, it's just like laying, pictures over one another, and some of them are slightly see-through. If you have something that is 255 over anything else, there will be no blending. If you use just RBG, things are fully opaque. It assumes a 255 value. But why 255? The examples we looked at earlier use 0 to 1. Well, this is a computer representation issue, mostly done for speed. Because computers represent all data combinations of bits, and a bit can be either 0 or 1. Right? Binary. I'm sure most of you have been familiarized with this concept. It is quite popular of computers representing things in zeros or one very strictly at a very low level. But you can represent numbers by multiple bits. Here are a few. So what actually happens here is each bit in a set of bits is counted as a power of 2. So the lowest end bit will tell you whether it's 0 or 1, because it is, that number being 1 means that 2 to the power of 0 is included, which is 1. If it's 0, there is no 2 to the power of 0 included, which is a 0. Right? You can see here that 2 to the power of 1 means that you would add a 2 or not to the accumulated value. 2 to the power of 0 is add 1 or not. 2 to the power of 2 is add 4 or not. Right? And you can see a little table here. So 0 means no 2 to the power of 2. 0, no 2 to the power of 1. 1 means include 2 to the power of 1, which would have a total of 1. So doing something more complex here, if you had 0, 1, 1, so no to the power of 2, but yes to the power of 1 and yes to the power of 0, you'd add these numbers together and get 3. Right, so this is how we do basic whole numbers in computers. We call these integers. Any questions on this? I know we're getting a little more math heavy. We made a little switch. Okay. Bits, bytes, and pretzels. So computer hardware has been optimized over the years to handle chunks of bytes, so group sizes. So a 1-bit value is one of those 0 or 1 numbers. It can be 1 or 0, 2 to the power of 0. But if you have 4 of those, like we dealt with, well, I guess we'd have one more, 2 to the power of 3, which would be 8. So you can represent numbers from 0 to 15. Is 4 bits. That's known as a nibble. 8 is a byte. 16 is a word. 32 is a double word. 64 is a pretzel. You don't really need to know those terms, but these are very common things like how many of you played the Nintendo 64? Commodore 64? Any of these 64 consoles that were very popular for a while? Okay. Those are the bit size, like how much like each representation chunk that the processor could use. That's how many bytes it could have. And for a long time, like increasing this number of bytes and doing it fast and efficiently for computer hardware was the name of the game. That was how we got speed. Now it's less of a deal. There's standard 32-bit and 64-bit things. You may have like in Windows tried to download an application. You had to choose between like 32-bit version of it or 64-bit version of it. So we're still working through the final treasures of that. But almost all modern processors are 64-bit now. So 1 byte is 8 bits. And it can hold 256 values with those 8 0 and 1s, interpreting them just like we did before. So here, all 0s is the 0 value. All 1s is the 255 value. So we'd add up 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, power of 3, power of 4, power of 5, power of 6, power of 7. And all that would, all these would equal to 255. Where this would be 128. 2 to the power of 7. So 128, 64, 32, 16, 8, 4, 2, 1. That was pretty fast over. You can read these slides if you want to experience this a little more. Happy to talk about this later. We will have some light information about this on the exams. So something good to know. This is a baseline representation that computers know that your art will be filtered through. All right, so now I want to talk about something practical. Save image.jpg. This is a special processing function, a special processing command. And it simply will save an image in your project directory called image.jpg of whatever you have drawn on your screen. When this function's called, it will save that screen image, the image of that screen, as a JPEG to your project folder. And let's say you want to, anytime you press the mouse, save an image, like we'll be doing for assignment 1, and like we'll be doing for the lab. There's a special set of commands, a special function there, or a special command called mouse pressed. So anytime you press the mouse, the system processing will automatically detect it and call this function for you. It'll call this block of code. In this case, every time you press the mouse, you'll save an image. Now, here the image name is the same, so every time you press the mouse, it'll rewrite the image that's there, and you'll get the last time you pressed the mouse button will be the last image saved. But sometimes you want more. Sometimes things are animated and moving, and you want to have a few more frames. Or maybe you want to have a flip book, something like that. So mouse pressed, it's a good way to do this. But we also have ways to save sequences of images, which will be handy for you when doing your work. So this is a little bit a magical incantation, a little bit of work that processing does on your behalf. So instead of using save image, you can use save frame. And save frame is different from save image in that it looks at the image name that you pass in. And then it will automatically look for 3 £signs or 3 hashtags in a row. And then it will, it'll automatically fill those in. So the first one you press will be 001, I believe. Then every time you save frame after that, it'll keep counting up those numbers. So you can easily fill up your directory pretty quickly if you have like a large window size and you put this in a place where it gets called too often. So something else I want to note about these two images are the double quotations here. Those double quotations we'll talk about later, but those are called strings. This is when you want to say, hey, don't interpret this as a command or a command like mouse pressed or save. You want to interpret this as a string of numbers, as something you want, an actual set of letters that you want to use somewhere else. And this is called in data structure terms a string, or meaning a string together set of characters. And that's how you say start the string with quotes and then end the string with quotes. So notice the sequence of letters that you want to associate with save, so the file name that you want to associate with save is everything between those 2 quotes. So the same with save frame. Now with numbers, you don't have to worry about it. Numbers you can put in directly, but strings are different. You have to make something that's a string look different than something that looks like a command. And we're just using raw text, so this is the way to do it. Okay, now we're going to get a little more, some more interesting round with translate. So this moves the origin. So remember last class when I told you that 000 is the top left? Well, let's say you want to start drawing in another region and you want to simplify the math. Or let's say you want to recenter your world so that the middle is the origin. Like let's say you want to do some cartographic drawing or some spirals. And it's really handy to have 000 match your math to be in the center. Well, this is how you do it with translate. Translate makes 0 change by x and y value. So if you had a screen of, if you had a window size of 200, 200, or 400, 400, you could translate to 200, 200, and then 000 would be the middle. Negative y would be going up, positive y would be going down, negative x would be going left, and positive x would be going right. So there's another term for this. It's transformation state. And this is one of the areas of that is a little more nuanced that really helps folks doing visual code, visual processing, making art on screen matter. So let's say you had I don't know if you've ever played a video game, they have a screen, a TV inside the game, there's something happening on that screen. Well, often there will be a set of translations that will say, hey, the thing you're drawing this screen, it has its own little screen space. And then it'll do that command there without having to like modify, like know exactly where you are in the world, where exactly it is on the screen. The transformations help handle that complexity. All right, this is back to our pixel grid view of the world, where 0, 0, 0 is at the left, top left. 0, 1, 2, 3, 4, etc. 0, 1, 2, 3, 4. So let's take a look at this. So we also have rotate. So you can take that ellipse and skew it. So rotating is in, using your trigonometry, takes an angle value made in radians, right? 0 to 2 pi for a full twist, where pi is 180. For those of you who are uncomfortable with radians, we'll actually, for now, use rotate. There's a radian command which will translate degree values into radians. So the example here, rotate. If you want to rotate by 20 degrees, simply say, hey, use this radians function, this radians command, which will take radians and spit back out degrees. Or I'm sorry, take degrees and spit back out radians, which is what rotate uses. Right, so this is how you can have one command take information like this 20, do something with it, like map it to radians, and then spit it back out. So this parameter list rotate will take whatever radians 20 spits out and operate with that. And pivot is relative to the origin of the object. This is also why it's good to have rect modes. So if you wanted to rotate a rectangle, you want the rect mode set to center, so it rotates around the center instead of the default, which is top left. So you'd rotate around the top left and your square would be rotating around its top left corner. Right, so thinking about where your centers are, where your origins are, can really help you draw what you want to draw. Any questions about this? All right, I'm going to send out some code examples after class today, and we'll talk about things about this in the lab as well. So more transformation state. So if you think of stroke as setting the color of pen that an outline is drawn with, you can similarly translate, rotate, and set the state of the origin. Right? So just like stroke and fill, translate and rotate can set the next thing you draw as properties. So if you want to, like, let's say, rotate, if you're like, you have this, you want to make some dice on the screen, like you're rolling like your Dungeons and Dragons, like you got your D12 that you're trying to roll, your 12-sided die. And you want to make sure that as it rolls, all of the numbers that you draw on the faces match the rotation that the die is flopping around with. Right? So this is, when you draw the dice, you can set its rotation, start drawing its sides, because the rotation stays, and that transformation stays, you can now simply use your normal, like a 0 to 1 coordinate space that you would normally draw a correct, like an up-facing, non-moving, stationary, canonical version of that 20-sided die with. You can continue using that same code as it tumbles. Because as it tumbles, that new orientation that it tumbles in is transformations and rotations that you set. So this whole idea of having transformational state really matters, right? Or let's say you simply want to draw a square that has a circle inside of it for some reason, and you want that to rotate. Well, by setting the state, you can simply draw the rectangle, or the rectangle with center set to like to rect mode set to center. Draw the rectangle, draw the circle, and that's your drawing code. And then before that, you can set all the transformations and rotations and translations and rotations that you want. And then that code will still continue to draw those things in the same proportion, the same relative locations to each other, but the whole thing will tumble and spin and move. So translate updates the position of the origin. Rotation updates the orientation of it. So like if you have your graph paper and you turn your graph paper, that's the same thing as rotating the origin. It's the same as using the rotate command. Now, like we said, default origin is in the upper left corner, 0, 0. X increases to the right, Y increases as you move down. Translate and rotate, update this, right? If you wanted to have a normal orientation, like if you're doing some graph drawing and you wanted -1 to go down again, you could rotate the whole thing by 180 degrees, and then you could flip it. There's a couple things you do. You'd have to flip it as well. But then you can return back to your classic graph paper orientation system. All right, so here's some problems we can look at real quick. So here we have a grid. What we want to draw is a rectangle, this orange rectangle. We want to make sure to draw it at values 2, 3. I'm sorry, 3, 2. So 3 being the x value and 2 being the y value. All right. With this translate, how do you think we'd do it? Yes.
2, 3.
Exactly. Well, 3, 2.
3, 2.
Yeah, x goes first, and then y.
Okay.
Yeah, so if we put 3 and 2 here in this translate function, then the fill and the rect with all the fill just had a color of GB, a blue. I should change this. And then the rectangle would be drawn at the new origin 0, 0, and then have a width of 100 and a height of 200, right? And so this new origin, now 0 and 0, moves to here. That's what we're doing with the translate, 3, 2. So now 0, 0 is moved, so 3 over and 2 down. Okay. Now with this chunk of code here, I should turn off that embedding. All these should be on the same line. I had hanging indented for some reason in the text block that I was using in PowerPoint. Pardon me. All these should be the same, indentation. We have a translation 100, 100. What translation would we have to do to draw at 3, 2?
-98, -97.
The other way around, -97 to get 1. Oh, so 3 has to be the result. So 100 minus 97 is 3. 100 minus 98 is 2. So that would be -97 filled into the first portion of the command, which is how far we have to move it to the left, and then the origin to the left, and then we want to move the origin 98 up. So negative, keep losing my mouse, there we go, -98. But it's going, there we are, -98. Right, so we move the 0, 0 would now be moved to 100, 100. But we want to draw this thing at 2, 3. So that means we need to move it left and move it up quite a bit. Does it make sense? Any questions on this? Yeah.
How do you determine whether or not the translate is going to affect the origin of the entire graph versus the origin of one object?
It's all about ordering. So where do you draw it after which transformation calls? And there's ways in managing this that we'll talk about with push and pop. So we will, there are ways to help sense make with this. All right, got a couple more. What would you put in this translate? So here the rectangle is drawing the top left corner. We're assuming that it's in top left mode. And it's being drawn at 200, 100 with a width of 100 and a height of 200. How do we get it back to 3, 2? What translate do we need? I know, I'm asking you to arithmetic. It's not even noon yet. Yes. Exactly. Negative 197, negative 198. Does that track for everyone? Excellent. What about this one? If it's at 0, 0, 200, 100, where do we fill in for translate and what do we fill in for rotate? Anyone got the translate part? This one's probably the simplest of the translation things we had to fill in. Yes?
32 and rotate 180.
3, 2, rotating 180 would do it. Right? If you notice here, the rectangle is 200, 100, and we want 100, 200. So we want to rotate it all the way around and then translate it. Now, also, it could be a little tricky. We'll map that out. We'll see if that actually works in the lab. All right, so the last thing we'll touch on here and then head over is commands like rotate and translate. They set a state, right? Just as we've been talking about these examples, they're relative to one another. So calling translate 100, 0, and then calling translate 50 would have the same result as calling translate 150, then 0. Right. They're additive operations that scale, that act sensibly. Now here is the nuance part. So push matrix. This actually saves the current state of your transformations. So you have like something that you want to draw, some orientation you want to draw, and then you want to sort of like save that for later use. You push it onto a stack, so it's a bit of memory that saves it. You can think of it like as a stack of plates, and you keep pushing a plate, putting a plate on top of the other plate. You often see these in like the dining halls where you pick up a plate and another one will pop up. It's a classic stack. First in, last out. Now, push matrix puts a configuration, a plate configuration, something, all your fills, your strokes, your translates, your rotations, puts it down the stack. And then you can still change the state. But when you want to go back to what that was before, you can do pop matrix. And so when you call pop, the thing you pushed will come back exactly as it was. So all the changes that you made after you pushed, you can do a bunch of drawing and a bunch of rotation and stuff. And then when you pop, all those will go away and it'll be back to the state, the configuration that you pushed it. So this will be handy, and that'll be, there's a question on assignment 1 about using push and pop. And so here's an example. You can push the matrix, translate, rotate, do whatever, pop the matrix, and you go back to default. All right, that's what we got for today. Let's head over to RDNX. For those of you who aren't familiar with RDNX, find someone who is familiar with there. Armfreet, are you biking or walking?
I'm walking.
Okay, well maybe follow Armfreet. I'm biking to go get things set up.